Okay, let me know if there is anyone they're not joining because I don't want to be dragging for long. I just want to finish our chapter 4. That's it. So that we can start to discuss our tutorial on Wednesday later. Okay, let me present my screen. Okay, so just to recall back what we have discussed the last lecture session. So I have started to discuss the black box test design technique, and I have started with the equivalence partitioning. Okay, so we will have equivalence partitioning and then boundary value analysis, and then under the logic based testing we will have another two more. So I have already discussed the equivalence partitioning where we need to identify the equivalent classes, which is the valid equivalent classes and the invalid equivalent classes based on the given requirement. Then after that, we need to define the test cases where for each of the equivalent classes, we need to come up with the unique number of class. So that is what we call as a test case. Okay, so I have go through this example, okay, where we have four different valid equivalent class. Okay, and normally the scenario or the requirement will be given for all the valid classes. Then from the scenario we need to identify the minimum and the maximum range. Okay, so this table I have mentioned that we will have another one more column which is for the expected output. Okay, so VEC stand for valid equivalent class, and each of it we will use a unique numbering 1, 2, 3, 4. So it means we have total of 4 valid equivalent classes, and then according to the given requirement. So this is how we break the classes. So 0 until 14999, then 15,000 until 20,000, then 20,001 until 24999, then 25,000 and above. So I have mentioned that since we want to continue this technique into boundary value analysis, we must not leave it open like this. We must indicate where is the maximum value should end. So since our invalid equivalent class here already said anything more than this value, it's considered unrealistically high sales price. So we can use that as uh, the minimum, sorry, the maximum. So it suppose should be less than equal to, because here is more than. Okay, so for each of these classes, there will be one representative value, and the expected result is already given here, where the first one is 0% discount, the second one is 5% discount, then the third one is 7% discount, and the fourth one is 8.5. So that is what we suppose should have on the last column here. Okay, then for the invalid equivalent clauses, the same thing, but the scenario normally will not give us the classes or the range. Okay, so we need to think out of the box where whatever below the minimum and whatever more than the maximum consider as the invalid equivalent clauses. So when we are using a range of values, we concentrate on the invalid from the range given. No need to give like what happen if it's using characters, what happen if it's using any special symbols. All this is not really relevant here. So we just cover whatever below the minimum, whatever more than the maximum, it is considered enough equivalent clauses for the invalid. So IEC stand for invalid equivalent clause. Then we have 2, 1 and 2 representing the unit. So here the representative value, and for the expected output for the invalid equivalent clause, we don't have discount. Okay, so we need to indicate what will be the error message. So for example, the first invalid equivalent class, whatever below 0, it's considered wrong sales price. So we will indicate the error message is wrong sales price. Then for the second class, we will indicate the error message as unrealistically high sales price. Okay, so that will be the expected output. Okay, then I have started to discuss about the boundary value analysis. So for the boundary value analysis, from the valid equivalent clause here, because when we said boundary value analysis, we need to have a range of clauses. It means the minimum and the maximum. So that's why only the valid equivalent clauses will be used to identify the boundary value analysis. So we don't do anything with the invalid equivalent clauses. Okay, so this is just a simple example which I have discussed last lecture, where the text field is accepting values from 18 to 56. So this format, this table, you need to follow it. Okay, for boundary value analysis, you need to have one column indicating the minimum -1, then another invalid which is maximum +1, and then for the valid we have these four values, which is the minimum, minimum +1, maximum -1, and the maximum. So this will be the 6 values which you can get for each of the equivalent clauses. It means for each of the valid equivalent clauses. So in here, you can see that we have a minimum boundary, which is the minimum 18, and then the maximum is 56. And then this will be the 4 valid values, which is the 18, 19, 55, and 56. And then 2 invalid value, which is less than the minimum, and then max +1. So it means one value from the minimum and the maximum, it's considered the invalid. So let's assume that from from these 4 clauses, if we want to identify the boundary value analysis, so it means we have 4 different clauses. For each of the clauses, we will have 4 valid values and 2 invalid values. Okay, so it means total of 24 values which we can use for us to prepare the test case. So it means for each of the classes we have 2 invalid values, which is one is less than the minimum, one is more than the maximum, and then 4 valid values which will be the minimum, the maximum, then minimum +1, and then maximum -1. Got it? Can understand? From these classes, we can actually prepare this. So for each of the classes, okay, we will have total of 6 different values. Because the reason why we continue from the equivalent classes to the boundary value analysis, because we want to see how is the border value has been correctly identified, because one value which is a valid value for one boundary equivalent class will be or must be invalid for another class. So if the value is actually valid for both of the classes, it means something is wrong. Okay, so for example, let's assume uh, let's assume I bring out the four equivalent clauses into the boundary value analysis. So let's assume I put as a table. I have four clauses, and then I have three border and the clause. Okay, so let's assume here is my equivalent clauses. Okay, don't forget it is actually only the valid one. Okay, then let's assume I put the boundary value. So here is the valid, which is the minimum plus 1, and then maximum minus. Okay, then maximum. Okay, so here will be invalid, which will be minimum minus 1. Sorry, my keypad is not working. Okay, then here is invalid, which will be maximum plus 1. Okay, so the class just now which we have is the first one, um, valid equivalent class 1, which was is it an image? Sorry, it's an image, so I need to type one by one. Okay, let's assume I just put for one, then you should do for others. Okay, so let's assume we have all the four valid equivalent clauses one by one. So I will be taking from here VEC1 until VEC4. Okay, so from here I need to identify each of these value. So the first one I have 0 as the minimum. So minimum plus 1 will be 1. Then what is the maximum value for this range? For this class, what is the maximum value? Is it 15,000? No, so be careful with the symbols when you are using. So the maximum value is 14999. So when it comes to maximum minus 1, 14998. So this will be the four valid values. Okay, then here will be -1, and here will be 15000. Okay, so this is the four valid values and the two invalid values for the first equivalent class. So let's assume I put the second equivalent class where it's actually start from 15,000, and then I have the X, and what was it? Sorry, okay, less than equal to 20,000. Okay, so if you see my second clause, so the minimum value will be 15,000, and then sorry, 15,001, then 1999, and then 20,000. So here will be 2001. So here will be 14999. Okay, so if you see, let's use this 2 as an example. If you see 1499 is actually a valid value for this equivalent class, the first one. And the same value will be invalid value for the second equivalent class. So it means the same value can be used for two different test cases here. It means here it will be a positive test case. Here it will be a negative test case. So this is showing that we have break the boundary correctly. Another one more will be, if you see here, 15,000 is an invalid value for the first class and 15,000 will be valid value for the second class. So this is how it supposed should be. If the value is actually becoming valid for the first class and the second class. For example, here my minimum is 14999. It means there is something wrong with our breaking of the equivalent classes. So that's why this boundary value analysis and the equivalent class work together, because from equivalent class we have a very less number of test cases because we just have one representative value. But for us to make sure that we are accurately testing the border value and so on, so we can actually ensure we are correctly using the valid and the invalid value for different test cases or different situation of the values. So that's why boundary value analysis always come together after we have done the equivalent class to confirm if we have break down each of the equivalent classes with the correct boundary value or not. Okay, boundary value can be on its own, but when it comes to equivalence partitioning, we always try to bring it together with the boundary value analysis. Okay, so this will be the table format for boundary value analysis. Okay, so all this is just an example. This is using the grade and also the marks, okay, to show the border value for each of the grade. So the grade is actually the expected output, and then what is the classes here. Okay, so anything less than the minimum, anything more than the maximum should be the invalid. Okay, since it's a number, of course we don't have the end, but we don't need to test every impossible numbers. Anything one level down or one level up, it's already sufficient to show the boundary is being covered correctly. Okay, so this is the table based on the test case. Okay, so nothing much. Okay, and then this one is actually the boundary value analysis for the previous example just now, the one we discussed just now, for this one. Okay, so it's just to clear up the symbols and what will happen. So be careful when you are preparing. Okay, when you are preparing the symbols, so this is less than, okay, less than, equal to, and then this is less than, more than, and then this is more than, equal to, this is equal to. So just be careful when you are using this symbol. For example, we refer back to the equivalent classes just now where we actually have used less than. So let's assume if you are not comfortable of using less than, then you can directly put less than equal to 14999 just to avoid confusion. There is no mistake here. You can use less than or you can use less than equal to, but make sure the value must be based on the given scenario. So you must read to understand where is the value. So you need to know the correct minimum and the maximum value. So you want to use a less than or less than equal to, it is up to you. Okay. So this is just to show that each of this symbol, okay, it will be causing the true and false. So if you see, this is actually three different border value. So the scenario said 25,000. So 25,000, this is actually -1. This is maximum +1. Okay, so based on the symbol, this will be true, this will be true, false, and then based on this symbol, these two will be true, this will be false. So this is just to recall back that make sure when you prepare the table, you are breaking the border in a correct value. Okay, so nothing much. Okay, any question before we will start with the cause effect graph and decision table? So the pairwise testing, I will just go through briefly. We are not going to cover for your midterm, for your assignment, and also for your final exam. We will not cover. Okay, clear? So far the boundary value analysis and the equivalence partitioning. Okay, so let's move with the cause effect graph. So this cause effect graph and decision table, they come in a pair. This is one pair. So even though equivalence partitioning and the boundary value analysis, they can work on their own, but when it comes to midterm, final exam or assignment, we will use both of them as a pair. So it means after you're done with the equivalence partitioning, it will continue with the boundary value analysis. So the same thing goes when it comes to cause effect graphing and also decision table, it will come together. So based on the cause effect graph, you will produce the decision table. So it work as a pair. Okay, so let's see what is this cause effect graph first. So cause effect graph is actually where we have a condition which is the cause, okay, and for this condition, okay, when they are connected, okay, logically, what will be the effect? It means what will be the output happen. Okay, so this cause effect graph, it's actually use the logical relationship between the causes, something like the input, and also what will be the effect. Okay, what will be the output for this input, what is the output? So the same thing for this cause, what will be the effect? So the connection of these two is what we call as a cause effect graph. Okay, so normally the scenario will be giving you the condition and also the effect. So these conditions or these causes actually need to have a combination. Okay, so normally these causes or the condition will be connected using the logical operator. So as usual, we just recall back what you already know, which is using the AND logic, OR logic, or NOT logic. So when this condition or the causes has been combined, and according to that, what will happen to the what will happen to the effect? Okay, so it means it will be true or it will be false. Okay, so something like this. So C is presenting the cause. C is stand for cause, E stand for effect. So when you are labeling, you will label them this way. Okay. So here we have the and, here we have the or, we have the not, we have the mutually exclusive. Okay. So when we said and, it's the same thing. When both actually are true, okay, then the effect will be true. So the symbol for the and, you have to use this. Okay, so it means when the cause one, cause two, both of them, they are true, then this effect will be true. For example, something like that. Okay, it's depend with the requirement. Okay, so here we are just showing how to draw the graph, not following any requirement yet. I will show you example later. Okay, so here this will be for the or logic. Okay, it's just the opposite of the and. Okay, where if any of the C1 and C2 is true, okay, either one, so automatically the uh, E1 will be true. Okay, then this symbol, can you see this symbol, or you can draw it small also, no problem. Okay, this symbol is actually showing the not. So it means if the C1 is true, E1 will be false. If C1 is false, then E1 will be true. So it will be on the opposite. So another one more is mutually exclusive. Mutually exclusive, the drawing will be actually on the left side of the condition. When you draw, the condition will be on the left, the effect will be on the right, and when there is any situation, okay, later I will show you one example. So this will be outside of the left. Okay, so this dot dot line is showing the mutually exclusive when only one effect can be true at one time. It means there is no possibilities for both to happen. That is when we will use the mutually exclusive. Okay. Okay, any questions so far about the symbol? So it's just to recall back. So we use the and, we use the or, we use the not, and in some situation you might need to use mutually exclusive. So this is the symbol for and, this is the symbol for or, this is the symbol for not. Okay, and this is the dot dot line at the back of the cause will be the mutually exclusive. Okay. Let's see the scenario given. So there is a situation where the print message is a software that read two characters. Okay, and depending on their values, messages must be printed. So if you see, the cause is actually there is two characters, and then the effect should be the messages. Okay, so let's see how the causes has been divided. So the first character must be A or B. Okay, this is the first character must be A or B. It means it cannot be both at the same time. This is what it's mean by mutually exclusive. Only one can happen at a time. It is either A or it is either B. Cannot be both happen together. Okay. Then the second character must be a digit. So the first character must be A followed by a digit, or it is B followed by a digit, because only two characters. Okay, then if the first character is an A or B and 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 the second character is a digit, then this will be the effect. File must be updated. Okay, so this is a first situation. Second situation, if the first character is incorrect, it means it's not A or B. The message X must be printed. This is second situation. The third situation is if the second character is incorrect. It means it is not a digit. Then message Y must be printed. Okay, if you see, compared to equivalence partitioning boundary value analysis, cause effect graph is more to this type of situation, or it is more to action based situation where there is no range of minimum maximum values. This is more to, if this is the input, what will be the output? If you do this, what will be the output? If this is the input, what happened? So more to action based scenario.